As Banfield viewers are well aware, not all mysteries are whodunits. Some of the biggest mysteries in the universe are all about other questions, like the question facing skywatchers tonight. What is it?
A Manhattan-sized interstellar visitor is on a collision course with destiny, its name 3I/ATLAS, the third confirmed wanderer from outside our solar system. Unlike the asteroids and comets we've cataloged for centuries, this object is not native to our cosmic neighborhood. It was born under another star, forged in conditions alien to us, and it has traveled millions, perhaps billions of years through the void to arrive here. When it was first spotted, astronomers celebrated. After all, only two interstellar objects had ever been identified before: the cigar-shaped Oumuamua in 2017 and Comet Borisov in 2019. Both offered tantalizing clues about the chemistry and dynamics of other planetary systems, but they passed through quickly, leaving more questions than answers. 3I/ATLAS, however, is different. Its trajectory, once thought to be just another fast flyby, has shifted. Subtle gravitational nudges, outgassing jets of vapor, and the relentless pull of our star have conspired to bend its path inward. Now, a new alarm is ringing. A joint analysis by NASA and Harvard astrophysicists suggests that 3I/ATLAS may not escape back into interstellar space. Instead, it could plunge directly into the sun. The idea is staggering. A body from another solar system, carrying frozen chemistry and isotopes from a place we'll likely never reach, may end its journey in the furnace of our star. The event would not be subtle. If 3I/ATLAS slams into the sun's atmosphere, it will vaporize in a blaze detectable across the electromagnetic spectrum. Solar probes, space telescopes, and observatories around the globe could capture the spectacle in exquisite detail, turning destruction into discovery. And that is why astronomers are both worried and excited. The sun itself won't be harmed. The impact of even a city-sized comet is negligible compared to a star's mass. But the opportunity to observe such an event is priceless. It could transform our understanding of interstellar chemistry, solar dynamics, and even the history of cosmic migration. Before we explore the science, the risks, and the cosmic theater about to unfold, one thing is clear: this is not just another comet. 3I/ATLAS is a messenger from the stars, and its final act may be written in fire. The story of 3I/ATLAS begins with a flicker of light in the sky. Astronomers using survey telescopes noticed an object moving unusually fast against the backdrop of stars. Its motion didn't fit the familiar arcs of main-belt asteroids or the long, looping paths of comets from the Oort cloud. Instead, its orbit was hyperbolic, open-ended, meaning it was not gravitationally bound to our sun. That single fact confirmed it as something extraordinary, a visitor from another star system. Interstellar objects are vanishingly rare. For centuries, scientists assumed they must exist, since planetary systems constantly eject debris during their formation. But spotting one is like finding a single grain of sand blowing across the Sahara. The universe is vast, the sky is wide, and these wanderers move quickly. Until 2017, none had ever been observed directly. The first was Oumuamua, discovered by the Pan-STARRS telescope in Hawaii. Its elongated, almost cigar-like shape and lack of a typical cometary tail baffled astronomers. Some speculated it might even be artificial, though the prevailing view is that it was simply an odd fragment of rock or ice. 2 years later came Borisov, a far more conventional comet with a bright tail, but unmistakably interstellar in origin. 3I/ATLAS, named after the asteroid terrestrial impact last alert system that detected it, is only the third in this lineage. Its estimated size is staggering, comparable to the island of Manhattan. Unlike Oumuamua, it is active, showing signs of outgassing, jets of vaporized ice erupting as it approaches the warmth of the sun. Those jets are both a blessing and a curse to scientists. On one hand, they provide valuable clues about its composition, hinting at exotic ices and organics not common in our solar system. On the other hand, they make its trajectory unpredictable. Each burst of gas acts like a thruster, subtly shifting its orbit in ways difficult to model. From the beginning, astronomers knew this object was special. It is not just a rock, it is a capsule of alien history. The ices locked inside may carry isotopic ratios unique to its birthplace. Whether near a young star, on the fringes of a dense nebula, or in the frozen outskirts of a distant planetary system, to study it is to peek into environments we could never reach with spacecraft. But fascination soon turned to concern. Initial calculations showed it would sweep past the inner solar system, perhaps putting on a modest show. Then, as new data came in, the orbit refined, and the story changed. The sun's gravity, relentless and absolute, appeared to be dragging it onto a fatal inward path. This is where NASA and Harvard stepped in, combining observational power with theoretical modeling. What they discovered would reframe the entire conversation. NASA's strength lies in its instruments, from Earth-based telescopes to space observatories like the Hubble and the James Webb, to specialized spacecraft like the Parker Solar Probe. It's to track and measure celestial bodies is unparalleled. Every flicker of light from 3I/ATLAS, every shift in its brightness, every spectral line in its reflected sunlight was captured, cataloged, and analyzed. But raw data is only the beginning. To predict the fate of such an object, you need theory, mathematics powerful enough to account for countless variables. That is where Harvard's astrophysical community entered the stage. For decades, its researchers have built the frameworks that explain orbital mechanics, interstellar dynamics, and the subtleties of solar interaction. When NASA's measurements were fed into Harvard's models, the results were sobering. What emerged was not a neat trajectory curving out of the solar system, but a set of probabilities, many of which ended with the same conclusion. 3I/ATLAS might not escape. Instead, its path suggested a growing chance of collision with the sun. The collaboration between NASA and Harvard was critical because each brought strengths the other lacked. NASA's data streams are vast, but interpreting them requires a theoretical backbone. Harvard's simulations are elegant, but without precise measurements, they are guesswork. Together, they created a synergy that sharpened predictions. At first, some astronomers were skeptical. Orbital predictions are notoriously uncertain, especially for active comets. Outgassing can mimic tiny rocket engines, producing unpredictable accelerations. A small miscalculation can swing predictions wildly. Was this alarm premature? Yet with every new observation, the models grew tighter. The scatter of possible outcomes narrowed. And though there is still no absolute certainty, science rarely deals in absolutes. The probability of a solar plunge became increasingly convincing. Why does it matter? Because if 3I/ATLAS falls into the sun, it won't just be a spectacular show. It will be a once-in-a-lifetime scientific opportunity. No interstellar object has ever been observed meeting such a fate. The physics, chemistry, and solar dynamics it could reveal are invaluable. And thanks to this collaboration, astronomers now have time to prepare, to point every instrument they have, and to make sure no data is lost when the final act unfolds. When astronomers speak of trajectories, they aren't just drawing straight lines across a star chart. The path of an interstellar body like 3I/ATLAS is shaped by a complex interplay of forces, each pushing and pulling in ways that can change destiny. At the center of it all is gravity, the sun's inexorable attraction which dominates everything within billions of miles. Initially, 3I/ATLAS seemed poised for a typical hyperbolic pass. It would enter the solar system, curve around the sun, and slingshot back into the darkness of interstellar space. That's what gravity usually demands, a bending of the path, not a surrender. But with each new refinement, its course began to look less like an escape and more like a spiral. Several factors are at play. First, there is the gravitational influence of the planets, especially Jupiter. This gas giant acts like a cosmic gatekeeper, often steering comets into new orbits or hurling them out of the system altogether. For 3I/ATLAS, a close approach to Jupiter altered its velocity just enough to shift the odds toward capture. What might have been a fleeting visit now looked like the start of a deadly inward fall. Second, there's radiation pressure. Sunlight isn't weightless. Photons carry momentum. As they strike the surface of a comet, they nudge it ever so slightly away from the sun. Normally, this is minor, but when combined with other factors, it can change the timing of a pass. Then comes outgassing. As 3I/ATLAS warms, frozen volatiles inside it boil into jets of gas. Each jet acts like a thruster, adding unpredictable accelerations to the object's motion. This is the most frustrating factor for astronomers. You can model gravity with precision, but predicting when and how a comet vents its ices is like predicting the crack of ice on a winter pond. The current consensus? The sun is winning. Instead of skimming past, 3I/ATLAS may plunge straight into the corona. Some simulations suggest it could disintegrate before making contact, shedding fragments that individually streak into the sun. Others predict a single fiery impact. Either way, its trajectory now points inward toward what may be the most spectacular solar event of the decade, To grasp what might happen when 3I/ATLAS slams into the sun, imagine dropping a snowball into a bonfire. Except the snowball is the size of Manhattan, and the fire is a sphere of plasma 100 times larger than Earth. The scale defies comprehension. As it nears the sun, the heat will become unimaginable. The surface temperature of the sun's corona reaches millions of degrees Fahrenheit. Long before 3I/ATLAS physically collides with anything, radiation will boil its surface, peeling off layers of gas and dust. Outgassing will intensify, jets blasting in all directions, possibly breaking the body into pieces. But if the nucleus remains intact until it plunges into the corona, the effect will be explosive. The kinetic energy alone is staggering. Traveling at hundreds of kilometers per second, 3I/ATLAS will release energy on impact comparable to millions of nuclear bombs. Of course, the sun is so massive that this is a pinprick to its overall structure. But locally, in the corona, the shock waves will be profound. We've seen hints of what this looks like before. Sun-grazing comets, small local ones from our own system, have plunged into the sun and produced bursts of radiation, ripples in the plasma, and temporary disruptions in magnetic fields. But none of those carried the alien chemistry of an interstellar object. 3I/ATLAS could inject exotic isotopes, rare ices, and organics directly into the solar atmosphere. For astronomers, this is a dream. Such a collision will produce observable phenomena across the electromagnetic spectrum. There may be sudden bursts of ultraviolet light, intense X-rays, and even gamma rays as the material interacts with the sun's plasma. Shock waves could propagate through the corona, revealing its density and structure in ways no probe could measure directly. The sun itself will become a laboratory, and 3I/ATLAS the catalyst. In the days and weeks following the impact, scientists expect to see lingering signatures, unusual emission lines in solar spectra, altered particle flows in the solar wind, and possibly disruptions detectable by instruments on Earth. Each of these will offer data points that could reshape our understanding of how stars interact with foreign material. Destruction is often the beginning of discovery. For all the drama of 3I/ATLAS's fiery end, what excites scientists most is the knowledge it may unlock. The object carries within it the chemical fingerprints of another solar system. Locked in its ices and dust are isotopes of hydrogen, carbon, nitrogen, and oxygen that may differ from those in our own comets. By analyzing the light emitted as those materials vaporize, astronomers can deduce their ratios and origins. For example, the hydrogen to deuterium ratio in its water could reveal whether it formed in a cold outer region or closer to a star. Carbon isotopes might suggest whether its birthplace was enriched by a nearby supernova or a quiet stellar nursery. These are not idle curiosities. They go to the heart of one of astronomy's greatest questions. How typical is our solar system? If 3I/ATLAS carries chemistry wildly different from our comets, it suggests that planetary systems form under a wide diversity of conditions. If it's similar, it strengthens the case that our system is not unusual, and that the processes that built Earth may be common across the galaxy. There's also the sun's response to consider. Every time fresh material plunges into its atmosphere, scientists gain a rare opportunity to test models of solar physics. How does the corona absorb foreign material? How do magnetic fields react when they're suddenly disturbed by a flood of dust and gas? These aren't just abstract questions. The sun's behavior has direct consequences for Earth. Solar storms can knock out satellites, disable power grids, and disrupt communications. By studying an event as dramatic as 3I/ATLAS's potential plunge, researchers can refine their ability to predict space weather, a field that's increasingly vital in our technology-dependent age. Finally, there is the sheer uniqueness of the opportunity. We've observed sun-grazing comets before, but never one from another star system. This is a natural experiment that cannot be replicated in a lab, cannot be simulated perfectly on computers, and may not happen again for centuries. The chance to observe, record, and analyze this collision is, quite simply, priceless. In other words, 3I/ATLAS may be about to sacrifice itself for science. And if astronomers are ready, its death could answer questions we've been asking for decades, even as it raises new ones we haven't yet imagined. In the past, humanity would have been helpless to do more than glance upward and wonder. A bright streak in the sky, a sudden flare on the sun, and then nothing but speculation. Today, however, the story is different. Humanity has built tools specifically designed to witness cosmic dramas like the one 3I/ATLAS may soon stage. At the forefront is NASA's Parker Solar Probe, the closest man-made object to ever approach the sun. Designed to endure blistering heat and radiation, Parker flies through the solar corona itself, measuring plasma, magnetic fields, and charged particles in real time. If 3I/ATLAS plunges into the sun, Parker will be in position to sense the shock waves, particle outflows, and localized heating from inside the storm. For the first time, scientists may watch the sun's response from within, not just from afar. Alongside Parker, the European Space Agency's solar orbiter orbits just outside the corona, armed with instruments to study solar winds and magnetic structures. It can image the sun at multiple wavelengths, capturing the ultraviolet and X-ray flashes that accompany any massive disruption. Together, Parker and Solar Orbiter create a 1-2 punch, in situ measurement plus remote imaging. Back on Earth, observatories are preparing for their part. The Daniel K. Inouye Solar Telescope in Hawaii, the largest solar telescope ever built, can resolve details as small as 20 kilometers on the solar surface. It will be ready to zoom in on the exact region of impact, capturing the plasma turbulence in breathtaking resolution. Networks of smaller telescopes, from Europe to South America, will coordinate to ensure continuous coverage so that no flare or emission is missed. And then there are the all-sky surveys, such as the Pan-STARRS system and the upcoming Vera C. Rubin Observatory. Though not solar instruments, they are invaluable for tracking 3I/ATLAS itself as it approaches. By refining its orbit, they help predict precisely when and where it may strike, ensuring the solar-focused instruments are pointed at the right place at the right time. Finally, artificial intelligence and big data pipelines will be critical. A solar impact will generate terabytes of information across multiple instruments and wavelengths. Sorting a signal from noise requires computing power capable of analyzing patterns in real time. Machine learning algorithms will detect anomalies, compare them with models, and flag the most significant events instantly. In short, the world is ready in a way it never has been before. If 3I/ATLAS ends its journey in the sun, humanity will not just watch, it will measure, record, and analyze every last photon. Beyond the fireworks, 3I/ATLAS offers something even more valuable, a lesson about the origins of planets and the diversity of star systems across the galaxy. Interstellar bodies like this one are not random. They are exiles, flung out of their birthplaces by violent events billions of years ago. Planetary systems are messy places when they form. Giant planets migrate, sweeping across disks of dust and gas, scattering smaller bodies in their wake. Some are captured, others collide, and many are ejected entirely. 3I/ATLAS is likely one of those unlucky wanderers, cast out of its home system before it ever had the chance to settle. It has been drifting through the Milky Way ever since, a fragment of another world carried on a galactic tide. By studying its chemistry, scientists hope to glimpse that other world. Does its water resemble ours, suggesting that habitable conditions may be common? Or does it contain exotic compounds that hint at alien environments unlike anything we know? The answers may reshape theories about how common Earth-like planets really are. There's also a larger question: how many such objects are out there? Until 2017, we hadn't seen any. Now, in less than a decade, 3 have been identified. Some astronomers believe that interstellar visitors may pass through our solar system constantly, thousands each year, but only a handful are large enough and close enough for us to detect. If true, then the galaxy is far more interconnected than we imagined. Planetary systems are not isolated islands, but archipelagos trading fragments across the void. For planetary science, this is revolutionary. It means that when we study interstellar objects, we aren't just learning about one comet. We're glimpsing the broader ecosystem of the Milky Way. Each visitor is a sample, a data point in a vast experiment stretching across billions of years and light years. 3I/ATLAS, by falling into the sun, may sacrifice itself to provide one of the richest samples of all. Every spectrum recorded, every isotope measured, every plasma wave detected will carry hints about where it came from and what that place was like. And in those hints, scientists may find new clues about how planets, and perhaps even life, emerge across the cosmos. In this drama, the sun is not just a backdrop, it is the central actor, the force that draws 3I/ATLAS inward, and the instrument through which we will learn. Its gravity has bent the object's path, its radiation has boiled its ices, and soon its plasma may consume the last fragments of alien material. This dual role, destroyer and teacher, is not new. Stars have always been both. They create the elements in their cores, forging carbon, oxygen, and iron from hydrogen and helium. They nurture planets with light and heat. And yet they also consume, pulling in comets, asteroids, and stray dust, erasing them in flares of brilliance. The sun's power is absolute, and 3I/ATLAS is simply the latest reminder. For scientists, this destruction is a gift. When foreign material collides with the sun, it acts like a tracer die in a medical scan. It reveals hidden structures, exposes flows of plasma, and highlights the magnetic skeleton that normally lies invisible. The shock waves from a disintegrating comet ripple through the corona, showing where it is dense and where it is thin. The emissions from exotic isotopes mark regions of heating and turbulence. Even the fragmentation of the object can map out the strength of tidal forces at different layers. And there are practical stakes. The sun is not just an academic subject. Its storms can cripple satellites, disrupt GPS, and plunge cities into blackouts. Understanding how it reacts to sudden injections of material helps refine models of solar weather. The lessons from 3I/ATLAS may one day protect our technology and infrastructure from the fury of our star. There is also a philosophical resonance. Watching a traveler from another star consumed by our sun is a reminder of scale. To us, 3I/ATLAS is immense, a city-sized block of alien ice. To the sun, it is less than a grain of sand. The imbalance is humbling, underscoring our place in a universe where forces beyond imagination rule. And yet, within that destruction lies creation. The data harvested from this event may inspire new theories, fuel new discoveries, and connect us more deeply to the cosmos. The sun, in ending the journey of 3I/ATLAS, will become a teacher once again, showing us not only the mechanics of plasma and gravity, but also the deeper truth of how stars and systems exchange material, energy, and meaning. Not all cosmic deaths are clean. For 3I/ATLAS, the finale may not be a single plunge into the sun, but a drawn-out unraveling, a slow breakup written across the solar sky. Fragmentation is the great wild card in cometary science. Some comets hold together until the very last moment, smashing into the solar atmosphere in one brilliant burst. Others disintegrate long before impact, scattering their remains into diffuse clouds that slowly evaporate. Which fate awaits 3I/ATLAS depends on a hidden detail we still don't know: the integrity of its nucleus. If 3I/ATLAS is a monolithic block of ice and dust, it may endure the tidal forces, spin rates, and outgassing stresses until the sun's corona tears it apart in a single, spectacular event. The release of energy would be sudden, concentrated, and brilliant, a flare that solar telescopes would record as a sharp spike across multiple wavelengths. But if it is a loosely bound rubble pile, a common structure among comets, the story will be different. Jets of gas could spin the nucleus unevenly, pulling it apart piece by piece. Each fragment would take its own trajectory, some vaporizing in the corona, others plunging deeper. Instead of a single pulse, astronomers would see a cascade, fragment after fragment lighting up, like sparks falling into a fire. This distinction matters. By observing how 3I/ATLAS breaks apart, scientists can deduce its internal structure, knowledge we could never gain otherwise. Was it compacted under high gravity near its birthplace? Or was it a fragile survivor of a chaotic ejection? Do its layers reveal different chemical histories, or is it uniform throughout? Every shard tells a piece of the puzzle. There is also the possibility of surprises. Some sun-grazing comets have split dramatically, with fragments as large as skyscrapers surviving long enough to streak visibly before fading. If 3I/ATLAS produces such fragments, telescopes may capture images of alien icebergs diving headlong into the sun, each one a messenger from a lost world. In the end, fragmentation is not failure. It is opportunity. Whether 3I/ATLAS shatters early or holds together to the last, the process will give astronomers the ultimate gift, a window into its hidden heart, and by extension, into the mysteries of planetary systems far beyond our own. The journey of 3I/ATLAS is almost over, though in cosmic terms, it has already been a saga beyond imagination. Ejected from its birthplace perhaps billions of years ago, it has crossed light years of interstellar space, silent and unseen. Now, by chance and by gravity, it has arrived here, at the edge of our awareness, in the final act of its existence. For scientists, it is a treasure trove, a rare sample of another star system delivered directly into our cosmic backyard. For observers, it is a spectacle, A reminder that the heavens are not static, but alive with motion, violence, and transformation. For humanity as a whole, it is a lesson in humility. A world-sized block of alien ice, traveling faster than any spacecraft we could build, is still powerless before the gravity of a star. The sun will barely notice its meal. Its mass will not change, its cycles will continue, and its light will shine just as it has for 4.5 billion years. Yet for us, the moment will be unforgettable. Our telescopes will record the flare, our probes will ride the shockwaves, and our computers will parse the signals into knowledge. Out of destruction will come insight. Out of an ending will come beginnings, new questions, new models, new connections across the stars. And beyond science lies poetry, a traveler from another world, ending its voyage in ours, an emissary from a foreign sun, consumed by our own. It is a reminder that the galaxy is not a series of isolated islands, but a vast, connected ocean where material drifts, collides, and transforms. We are part of that ocean. We are shaped by it. And in moments like this, we see the currents clearly. NASA and Harvard have sounded the alarm, not of danger to Earth, but of opportunity, a once-in-a-lifetime chance to witness the universe teaching us in real time. The countdown has begun. Whether 3I/ATLAS fragments gently or dives in one incandescent plunge, the end is certain. Its death will be our discovery. Its silence will become our story. The cosmos writes in fire and gravity. Soon, in the furnace of the sun, another chapter will be written, and humanity will be there to read it.